I'm going to talk about a new result on sampling colorings based on a new spectral technique. Consider a graph with n vertices and maximum degree delta. A proper Q coloring is a coloring of vertices with Q colors such that edges and vertices aren't colored with the same color. So the problem is, can we sample a proper Q coloring uniformly at random? If the number of colors is at most the maximum degree, the problem is NP hard. But it is conjectured that if Q is at least the maximum degree plus a small constant, then we can sample a proper Q coloring almost uniformly at random in polynomial time. The problem that we study here is sampling proper edge colorings as opposed to vertex colorings. But here's a simple observation. The proper edge colorings of a graph G correspond to the proper vertex colorings of the line graph of G. So the line graph is defined as follows. For every edge in G, we have a vertex in the line graph and two vertices in the line graph are adjacent if the corresponding edges in the original graph share an endpoint. So the problem will be this. Given a graph G, can we sample a proper Q vertex coloring for the line graph of G? Keep in mind that if delta is the max degree of G, then the maximum degree of the line graph can be as large as 2 delta. So what is known about the sampling vertex colorings? So for general graphs, the best known result for a while was by Vigoda that said that if Q is at least 11/6 times delta, then we can sample a proper Q coloring in polynomial time. A recent result improves Vigoda's bound on Q by a small constant. Moreover, many have been able to get better bounds on Q for cases that the given graph is locally sparse. But the line graph is a locally dense graph. The question is, can we get a bound on Q that is significantly better than 11/6 delta? So a result similar to most of the previous work is based on a Markov chain called the Glauber dynamics. The states are proper Q colorings of the graph. Starting from a proper Q coloring, we uncolor one of the vertices uniformly at random, and then we look at the set of available colors that are the colors that aren't used by the neighbors of the vertex. And we choose one of the colors uniformly at random and recolor the vertex and end up in the next state of the random bucket. Now, the Glauber dynamics converges to the uniform distribution. And remember, the mixing time is time it takes for the distribution of the random walk to get close to the uniform distribution. According to a classic result, to say that the mixing time is polynomial, it is enough to show that the spectral gap is inverse polynomial. Now we're ready to state our main theorem. We show that if the number of colors is at least pi/3 plus an arbitrary epsilon times 2 delta, the spectral gap of the Glauber dynamics for sampling Q colorings of the line graph is 1/n to the order of 1/epsilon. So the chain mixes in polynomial time. This result is an improvement over the previous best result that required the number of colors to be at least 11/6 times 2 delta. So for the remainder of the talk, first I'm gonna give you a brief background, and then I'm gonna talk about our technique. Our technique is fairly general, and we hope that it will find its applications in other problems as well. And finally, I'm gonna briefly explain how we applied this technique to color. The main machinery that we use is called spectral independence. This machinery was introduced recently, but since then it has been used to break some long-standing barriers. Given a ground set U and a distribution pi over subsets of size n of the ground set, we define a matrix psi of pi as follows. For every x and y in the ground set, the entry x comma y is a measure of independence between x and y. Namely, it is the probability that y is in a subset S sampled from pi, condition on that x is in S minus the marginal probability of y. And now we say that pi is alpha spectral independence if the maximum eigenvalue of psi of pi is at most alpha. Another way to look at this matrix is that it's a random walk matrix times n minus 1 minus its first eigenspace. So if you didn't remove the first eigenspace, the maximum eigenvalue would have been n minus 1. But after removing the first eigenspace, we can hope that alpha is much smaller than n minus 1, perhaps a constant. Another thing to note is that this random walk is defined on the ground set, whereas the original random walk that has a stationary distribution pi is defined on subsets of size n. So this new random walk is much smaller and much more local. So let's see this definition in the case of coloring. The ground set is all vertex color pairs. In other words, each member of the ground set is an assignment of a color to just one vertex of the graph. And pi here is the uniform distribution over proper colorings. So let's compute one entry of psi. To compute the conditional probability, we look at all proper colorings that assign red to the vertex B. And there are 4 of them. And in one of them, vertex C is colored with yellow. So the conditional probability is 1 over 4. Similarly, we can compute the marginal term. And so the whole entry is minus 1 over 12. So if we compute the whole matrix, we can see that the maximum eigenvalue is 0.85. So we can say that pi is alpha spectral independent for alpha equal 0.85. So the notion of spectral independence that we've defined so far isn't quite enough for our purpose, and we have to make it stronger. So to do that, first note that if tau is a subset of the ground set, then we can condition pi on tau, and this will give us a new distribution. And therefore, psi is defined for this distribution. In the case of coloring, this tau is can be seen as a partial coloring of vertices. And to see what pi condition on tau is, let's look at an example. If tau is the assignment of red to vertex A, then it's not hard to see that pi condition on tau is the uniform distribution over proper colorings of this new graph G tau, using only green and yellow. Now we're ready to define the stronger notion of spectral independence. We say that pi is alpha star spectral independence if for all subsets tau of the ground set that have size at most n minus 2, and the maximum eigenvalue of psi for pi condition on tau is at most alpha. So instead of just bounding the maximum eigenvalue of psi for pi, we bound it for all conditional distributions. So I'm going to tell you how to use spectral independence to bound the spectral gap of the Glauber dynamics. Remember that spectral independence means that there are exponential many local matrices that have small maximum eigenvalue. Now, there is a theorem called local to global theorem that says that using this fact for these local matrices, we can say that the spectral gap of the global random walk is large. So in other words, if pi is the stationary distribution of random walk and it is alpha star spectral independent, then the spectral gap of the global walk is at least n to the minus alpha minus 1. So here the global walk is, for us, the Glauber dynamics. Now, what we're going to prove is that if the number of colors is at least 5 over 3 plus small epsilon times 2 delta, then for the uniform distribution on proper Q colorings of the line graph, we have alpha star spectral independence. And here alpha is a constant depends on epsilon. Now, once we have this, we can combine it with the local to global theorem, and we get polynomial mixing for the Glauber dynamics. So far, I've defined spectral independence, and I've told you that to get fast mixing, it is enough to bound spectral independence for the stationary distribution. Now the question is, what tools do we have to bound spectral independence? So most of the previous results on coloring either use correlation decay or coupling to bound spectral independence. But in our paper, we used a very different technique called trickle-down approach. So this approach was used in the problem of sampling matroid bases before. In our paper, we generalized the original trickle-down approach and applied it to coloring. Now, before stating our generalized trickle-down theorem, I'm going to briefly talk about the original Oppenheim trickle-down theorem. So this theorem is an inductive approach for bounding a spectral independence of pi. And it says that first choose C2 to be greater than or equal to the maximum eigenvalues of all base case psi matrices. So base case psi matrices are the ones that are for conditional distributions in which we condition on subsets of size n minus. And now for every I less than or equal to n minus 3, we inductively choose Cn minus I in a way that satisfies this recursive inequality. And then the theorem says that this Cn minus I times n minus I minus 1 provides an upper bound for the maximum eigenvalues of all psi matrices for conditionals in which we condition on sets of size I. Therefore, if we can recurse up to Cn, pi is alpha star spectral independence for alpha less than or equal to maximum of j minus 1 times Cj. Note that in the recursive inequality, if we didn't have that loss term, the score term, then we could have set all Ci's to be equal to C2. But now, because of this loss, as j gets bigger, Cj grows. It is not hard to see that if we can show that C2 is less than or equal to 1 over 1 plus epsilon times n, then this theorem implies that alpha is at most around 1 over epsilon. So in the case of matrix, for instance, this C2 is 0. So we're in a very good shape. But unfortunately, when C2 is larger than around 1 over n, we can't recurse up to Cn, and in our case, for coloring, C2 in the worst case can be a constant independent of n. So Oppenheim's trickle-down theorem gives us nothing. Now I'm going to explain how to generalize Oppenheim's trickle-down theorem so that we can apply it to coloring. So this matrix trickle-down theorem is our main technical contribution. And here the main difference is that instead of using a single constant C2 for bounding all base case psi matrices, for each tau, subset tau of size n minus 2, we choose a matrix m tau to upper bound psi of pi conditional tau. And then for all tau of size less than or equal to n minus 3, we inductively choose m tau in a way that it satisfies this recursive inequality, and this which is based on this expectation of all n matrices for subsets that have one element more than tau. Now, the theorem says that this n tau times n minus tau, size of tau minus 1, is an upper bound for psi of pi condition on tau. Therefore, if we can find this matrix m tau recursively for all subsets tau, then pi is alpha star spectrally independent for alpha bounded by this quantity in terms of maximum eigenvalues of matrices and taus. Now, another way of looking at this theorem, which can be considered as a simplified and weaker version of the theorem, is that to get constant spectral independence, we only need to show that the expectation of the maximum eigenvalues of base cases is good, as opposed to in the case of Oppenheim, that we needed all of the base cases to be good. Now I explain how we applied our matrix trickle-down theorem to coloring. First, I used a simplified, weaker version of matrix trickle-down theorem to recover the already known bound of Q greater than 2 delta for general graphs. So remember that a nice thing about trickle-down approach was that the only psi matrices that we needed to bound directly were the base case psi matrices. Here, the base case correspond to colorings of graphs with 2 vertices, which are either connected or disconnected. Now, remember that psi is a random walk matrix minus its first eigenspace. In the disconnected case, the graph of this random walk is the complete bipartite graph, and it's easy to see that the matrix bound can be set to be 0. In the connected case, the graph of the random walk is a complete bipartite graph minus a matching. So in each row, we lose at most 1 over number of remaining colors in the base case, which is at least Q minus delta. We show this quantity by beta. Now let's plug this in the simplified version of the theorem. To compute the expectation of base cases, note that a random pair of vertices are adjacent with probability delta over n. So here's where the crucial assumption that Q is larger than 2 delta shows up. So if you have 2 plus epsilon times delta, we can upper bound alpha by constant. And so the random walk mix is important. Now, let's see how we can get better than 2 delta for edge coloring. So a crucial observation about line graphs is that there are a bunch of, they can be seen as a bunch of random graphs loosely glued together. In other words, for each vertex of degree more than 1 in G, we have a clique in the line graph of G. And any 2 cliques in the line graph share at most 1 vertex. So I want to show the essence of our approach for line graph by proving a similar theorem for the simpler case of complete graph. Again, according to matrix trickle-down theorem, we want to first find matrix bounds for the base case psi matrices. Here, we crucially use non-diagonal matrix bounds. For complete graph, for any tau of size n minus 2, G tau is 2 adjacent vertices. It is not hard to prove that we can define the matrix M tau that upper bounds psi of pi condition tau as follows. It's a block diagonal matrix, and for every color, we have a 2 by 2 block on entries VC and UC. And so this block is a minus j plus I over beta. So the max eigenvalue is still beta. It's still 1 over beta. But the important thing here is that this matrix also has negative eigenvalues. Now, why is it important? Because it turns out that as we induct to get matrices m tau for taus of size at most n minus 3, the negative eigenspaces cancel out some parts of the positive ones, and the maximum eigenvalue remains small. So now, by matrix trickle-down, we get a good bound on the spectral independence. Modulo some technical difficulties, the to get spectral independence for the line graph, a similar idea works. And as I said before, once we have spectral independence, this can be combined by local to global theorem to get fast mixing. So here are some open problems to consider. First, using this matrix trickle-down machinery, can we get to the bound 1 plus epsilon times delta on number of colors? We can do that for complete graph using this machinery. And the technique seems to be generalizable, but we haven't been able to generalize them so far. But we hope that it's possible. Another question to ask is that can we apply this matrix trickle-down machinery in other problems, either for proving mixing time for Markov chains, or perhaps in other applications such as construction of high-dimensional expanders.